Hi, I'm LeAnn Zuniga from California State University, Los Angeles. This research was conducted at University of Hawaii at Manoa in the Department of Geology and Geophysics under the advisement of Dr. Ali El-Kadi and was funded by NSF's Research Experience for Undergraduates program in 2017. This research looks at dispersivity, which is a critical parameter in understanding how contaminants are transported through porous media through dispersion. Some questions addressed include: are dispersivity estimates consistent across methods? Are values of dispersivity universal for the duration of the breakthrough curve? Are dispersion values inversely related to media hydraulic conductivity? And is modeling accurate in simulating transport in all media? A non-reactive tracer was used to examine dispersion when contaminated water entered and exited the given porous media. Dispersivity values were then estimated by using techniques that involved calibrating an analytical porous media transport model until the model matched the breakthrough curve data from tracer tests. Estimated dispersivity values were then compared between the calibrated model and the breakthrough curve analysis software QTracer2. Dispersion occurs in porous media as the result of water flowing through different pores at different velocities and taking various flow paths that differ in length. Porous media used included commercial sand, beach sand, fine gravel, and a heterogeneous mix of 75% fine gravel and 25% commercial sand. A simplified approach was used to estimate dispersivity by using the simple equation in Singh's 2006 paper. A one-dimensional analytical porous media transport model was also used. These graphs show the dispersivity calibration with the modeling. The red line is the breakthrough curve from tracer tests, and the blue line is the curve that was fit by the model. These graphs show dispersivity across the breakthrough curve. The red line, again, is the breakthrough curve from tracer tests, and the blue line is the dispersivity values found through Singh's simple equation. These graphs show dispersivity and the dispersion coefficient using the numbers found through the calibrated model and then the numbers found in the QTracer2 software. The dispersion coefficient is the product of dispersivity multiplied by the water velocity. Correlation between the dispersivity values is fairly strong, meaning the model kind of worked. However, correlation of the dispersion coefficient values is not as strong due to differences in values of water velocity. The analytical transport model is able to accurately reproduce the ascent of the breakthrough curve, especially in homogeneous media such as the commercial sand and the beach sand, but is not as accurate at modeling the descent of the breakthrough curve, especially in heterogeneous media, such as the fine gravel and the heterogeneous media made. Dispersivity in tracer tests did not reach an asymptotic value as implied by Singh's paper in 2006, but changed with the development of the breakthrough curve, as seen in these graphs, and they changed dramatically. Understanding dispersion in porous media is important for the future of groundwater management and care. Not having a universal dispersion coefficient means that we cannot accurately model dispersion of a contaminant until the breakthrough curve is completed. If we have a way to be able to better understand dispersion and better be able to model it using simple equations and analytical models, field tests can be better implemented and we can better understand how contaminants move through aquifers. Thank you.